Welcome to this video. Today, we're going to learn one of the most important algorithms in machine learning, decision trees. They are simple, powerful, and widely used, but they also have a big problem. They tend to overfit. So first, we'll learn how to control that and how to properly tune decision trees in Scikit-Learn. What if a single tree is not enough? We combine many weak models to build something much stronger. That's where Ensemble Learning comes in. We'll explore ideas like bagging and pasting and see how they help improve performance. Then we'll build one of the most powerful models, random forest. Finally, models can learn from their own mistakes step by step using methods like boosting, leading to the successful XGBoost. We're going to cover a lot of exciting concepts today, so let's get started.
In Scikit-Learn, implementing most machine learning algorithms generally involves 4 key steps: loading the data, creating the model with the desired hyperparameters, fitting the model to the data, and finally making predictions. In loading of data, one of the key advantages of decision trees is that they require minimal data pre-processing. Unlike many other models, they do not need feature scaling or centering, and they can naturally handle categorical features. Although in libraries like Scikit-Learn, we usually need to encode them first. As we discussed earlier, when creating the model, we can tune its hyperparameters based on our needs. For instance, here, instead of using Gini, we can choose Entropy as a splitting criterion. We'll talk about these two in more detail later. Finally, these probabilities are typically used in something called soft voting. If you're not familiar with it yet, don't worry. We'll get to it later in the video. As you know, in a decision tree, the criterion for selecting which feature to split on at each depth is based on how well that feature separates the data. In other words, how pure or homogeneous the resulting nodes are. This is typically measured using either Gini impurity or entropy. Take a look at this image. We're based on 4 features: wind, temperature, outlook, and humidity. We want to decide whether the game will be played or not. Each of these features can be selected at the root node. For example, if we choose to feature wind, the classes are split in this way. When the wind is weak, in 7 cases, the match was played, while in 2 cases, it was not. The choice of which feature to use depends on calculating the feature's gain, which can be computed using either entropy or Gini impurity. We are not going to go into how entropy or Gini are calculated, as this video focuses on more important concepts. But keep in mind that the selected feature is the one that results in more pure or more homogeneous nodes. Here's the formula for calculating entropy and Gini index. As we can see in a binary classification problem, if all the samples in a node belong to the same class, either all positive or all negative, the entropy reaches its minimum value, which is 0. If the samples are not perfectly pure, the entropy increases. For example, if the class distribution is imbalanced, entropy takes intermediate values such as around 0.7, 0.85, or 0.45 depending on the proportions. When both classes are equally represented, the entropy reaches its maximum value, which is 1. Notice that higher values of entropy or Gini impurity indicate more randomness or disorder. And as we get closer to 1, the node becomes more mixed. Notice that entropy always reaches a maximum of 1, whereas Gini impurity reaches a maximum of 0.5. Back to our coding. Should you use Gini impurity or entropy? In practice, it usually doesn't make a big difference. Both tend to produce similar trees. Gini impurity is a bit faster to compute, so it's often used as the default. We know that a decision tree is an algorithm that can easily overfit the training data. So when defining the model in Scikit-Learn, we need to tune some parameters to help prevent overfitting. One of the most important ones is max depth. As shown in the figure, the larger the max depth, the deeper the tree can grow, the more nodes it can create, and the higher the risk of overfitting. On the other hand, if we set it too small, the model may underfit. There is no single best value for max depth. It is a hyperparameter, and in practice, one of the best ways to tune it is by using grid search together with cross-validation. Still, some people suggest that a very rough starting point could be around log 2n, where n is the number of samples. Also, please pay attention that none here means unbounded. In decision trees, Two important hyperparameters that help prevent overfitting are min samples split and min samples leaf. Let's start with min samples split. This parameter controls when a node is allowed to split. For example, in the left side of the figure, the node contains only 5 samples. If we set min samples split equals 10, this node is not allowed to split because it does not have enough samples. So this parameter prevents the tree from growing based on very small subsets of data. Now let's look at min samples leaf. This parameter works a little differently. It does not just control whether we can split or not. Instead, it checks whether the resulting leaves after the split contain enough samples. In the right side of the figure, suppose a node with 25 samples is about to split. One side would contain 20 samples, which is fine, but the other side would contain only 3 samples. If min samples leaf equals 10, this split is considered invalid, because one of the resulting leaves is too small to be meaningful or reliable. So the split is avoided, or in practice, the node will be pruned or rolled back. Look at this picture. On the left, the decision tree is trained with the no restrictions, and on the right it's trained with min samples leaf equals 4. It is quite obvious that the model on the left is overfitting, and the model on the right will probably generalize better. Similar to other hyperparameters, there's no exact value for these two hyperparameters, and the best value for them can be determined using grid search. But bear in mind min samples split should be at least twice min samples leaf, because a split creates 2 leaf nodes, and each of them must contain at least the minimum number of samples. The same concepts we discussed for decision tree classification are also relevant in decision tree regression. For instance, the following code demonstrates how a decision tree regressor can model a noisy second-degree function with and without min sample leaf.
Imagine you have a single tree trying to make decisions. You can prune it, control its depth, and carefully tune all its parameters. But at the end of the day, it is still just one tree, with its own limitations and biases. Now imagine, instead of relying on just one tree, you ask an entire forest. Each tree sees the data a little differently, makes slightly different mistakes, and captures different patterns. But when they come together and vote, their individual errors start to cancel out, and what remains is a much stronger, more reliable decision. This is the power of ensemble learning. Instead of trusting a single model, we trust a collective, and often the wisdom of the crowd leads to better decisions than any single tree ever could.
In Ensemble Learning, we train a bunch of really different models, like a logistic regression, a support vector machine, and maybe a random forest, all on the very same data. So then you get a new piece of data. What do? You show it to every single model in your group. Each one gets a vote. In this case, 3 models say class 1, and 1 model says class 2. It's simple democracy. The final prediction is whatever gets the most votes. In this case, class 1. Now that simple majority rules approach is called hard voting. If all classifiers are able to estimate class probabilities, or they all have a predict probo method, then you can tell Scikit-Learn to predict the class with the highest class probability, averaged over all the individual classifiers. This is called soft voting. It often achieves higher performance than hard voting, because it gives more weight to highly confident votes. The following code creates and trains a voting classifier in Scikit-Learn, composed of 3 diverse classifiers. And does it actually work? Oh, you bet it does. Just look at these numbers. You've got 3 individual models. The best one topped out at about 89.6% accuracy. Not bad. But when you combine them into a voting classifier, 90.4% accuracy. The group really is smarter than its smartest member. One way to get a diverse set of classifiers is to use very different training algorithms, as just discussed. Another approach is to use the same training algorithm for every predictor and train them, and different random subsets of the training set, when sampling is performed with replacement. This method is called bagging, short for bootstrap aggregating. When sampling is performed without replacement, it is called pasting. In machine learning, bootstrap refers to sampling the data with replacement. The term actually comes from the phrase pulling yourself up by your bootstraps, meaning building something from limited resources. And that's exactly what we do here. We repeatedly sample from the same dataset to create multiple slightly different datasets.
So far, we've learned how to control overfitting in decision trees and how combining multiple models can lead to better performance. In this video, we briefly touched on sampling methods, but we'll cover them in much more detail in the next video. In the next video, we'll take a deeper look at sampling strategies, see how they differ in practice, and implement them step by step in code. We'll also explore powerful methods like ADA boost and gradient boosting, and see how they build strong models from weak learners. If you found this video helpful, please consider subscribing to the channel and supporting my work. And feel free to share this video with anyone who is interested in machine learning. So make sure to stay tuned.